Hello, this is Math with Beth, and we're going to look at uninhibited population growth. This is part of calculus for most people. So first, we're just going to look at this fact about the derivative of this type of equation. So all they're saying here, because this is intimidating for some people because there's so many letters, remember this is just another way to say derivative. So these are saying the same thing. They're saying that there's only one type of function where the derivative equals some number k times the original function. So this is just another way to say that, k times f of x. So what type of function would have this kind of derivative is what we're about to learn. And it's only going to work if the original function is in this form, c e to the kt. A lot of letters. The c is just going to be some constant number. E is the letter E, which means 2.71, blah, 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 blah. It's a number kind of like pi, right? K is going to be a rate, so it's usually going to be a decimal, and T is going to be the time, depending on what we're talking about. Maybe it'll be years, maybe it'll be weeks. So this type of equation will always have a derivative where it ends up being K times the original function. And you should know that if you've already practiced doing derivatives with E, because all it's really saying is that you need to use the chain rule. Because remember, the derivative of e to the anything is itself. But then if there's something extra here, you'll have to use the chain rule to then do the derivative of that. And that's where you're going to get that k. So this really is nothing new. It's just a fancier way to say that the derivative of something with an e is going to end up being the same thing times this k because of the derivative of the top. So let me show you how they first ask these types of questions. So it might ask you to find the original function. So find the function that would satisfy the fact that the derivative equals 5 times a. Well, these a's here are our clue that we're going to call the function a. And since there's an x here in the bottom, it means there's going to be x's in it. So I'm going to call my function a of x. And now it must be, because it's using this rule, it must be in the form c times e to the kt. The only thing I know, though, is what k is. Because if the derivative is 5 times a, then 5 must be the k. So that's it. It's just basically saying that you understand that this type of derivative only happens if the original looked like this. So you can pause it and try number 2, or watch it again if you're confused. So in this case, my hint with these n's is that I'm going to call my function n, but this time instead of having x's, it has t's. That's fine. Because the derivative is some number times itself, I know it must be in the form c times e to the kt. It's just that my k must be that number. So these are the exact same. It's just that I use different letters depending on what letters they use to set up the derivative. That's it. So now let's do some larger problems where we'll actually solve more than just setting these up. So first, here is our equation for uninhibited population growth that we've already been talking about. Hopefully you know that the growth of e to the something would typically look like that, where it's just going to get larger and larger. That's why it's called uninhibited, because there's no max. It's just going to keep going up forever. This number in front is going to represent the initial population. E is just E, but K is going to be our rate. We're going to turn it into a decimal if they give you a percent, and time will be the T. So for this example, suppose P sub O, which just means like the original P, is invested in a fund, compounded continuously. That's your hint that you're going to use this equation with a rate of 7% per year. So that means our K is going to be 0.07, because that's what 7% is in decimal. That is, at any point, it is growing at the rate. So again, they're giving us this derivative equation, and that it is 0.07 times the P. So first they're going to say, find the function. So this is basically the same thing we've been doing. So I'm going to call my function P of t because of the P and the T there. I know that it's going to be some number C, but this time they said, write it in terms of P sub O. So that just means put that where the C normally is, because that's what they're calling the initial amount. E to the K, which we know is 0.07 times T. So there's my equation. P sub O, which is the original amount, which we don't know right now, times E raised to the 0.07 T. So now, suppose 10,000 is invested. So now they're actually giving me a number for that P sub 0. What is the balance after 1 year? So they're giving me the T. So if I now have the P sub 0 and the T, I have everything I need and I should be able to find this. So we're trying to basically find P of 1 because we're trying to find the answer after 1 year. So I put in my $10,000 times E raised to the 0.07 times 1. So put this in your calculator carefully. Make sure that this stuff is in the exponent spot. And then you should get $10,725.08. If they don't tell you what to round to, always do 2 decimals if you're dealing with money. So this is just a dollar sign here. So that is how much money we would have after 1 year. C, how fast is the balance growing at t equals 1 year? How fast is it growing is your hint that we need the derivative. Because anytime you're dealing with how fast something is growing or decreasing or a rate, you need the derivative. So the derivative of this would be, remember, it would be, so let's go back to the original equation. So the derivative of this, knowing that this is 10,000, would be 10,000 e to the 0.7 t, but then we would have to also multiply by that 0.07. So when you do this, you can do these two things first if you want to make it a little nicer. So 10,000 times 0.07 is 700. I should have known that. So 700 e to the 0.7 t is my new equation for the derivative. And they want to know how fast is it growing at t equals 1. So we really just need to go to the t and put a 1 into this new equation for derivative. So if you do that, you will get 750.76. So that is how much it is growing per year. So anytime you're using the derivative, you're finding some kind of rate. This is how much it's going up per year or per month, whatever the t happens to be. So in our case, it's years. So our balance after 1 year is growing at a rate of $750.76 per year. Okay, so let's try another one. It takes a little practice to get used to these. Talking about COVID-19, on March 1st, 2020, there was this many global confirmed cases. By April 26, 2020, which is 8 weeks later, there were this many global confirmed cases. So what they basically have given us this time is like 2 points. So they're basically saying at time 0, when we start, we have this many. And 8 weeks later, so at time 8, we have this many. So those are our 2 points. We can model the cases with the assumption that it will grow at this rate, which means we're dealing with our typical equation. Find the function that satisfies the equation, assuming NO, so the initial amount, is this, which we basically already know because of the fact that 0 gave us this, right? So our equation should be the initial amount, which we know, times e to the k, which we don't know, times t. So this is our equation, but we really need the k. So we need to do one more thing to figure out that k, and that is, now that we kind of have the equation, we can use this other point and plug in 8 for the t and this for the answer and see what we get for K. So if I plug in my 2.73 million, which is really this, and plug in my 8 for T, we should be able to solve for K. So first step is I'm going to divide both sides by the 86,000. Because anytime we have e to the something, we want to get that by itself. So that gives us this. I'm going to just round right now, but I'm really not going to round in my calculator. Because if we're going to round, we want to wait till the very end. So do you see how right now when I did my dividing, I got this long number? So I'm just going to keep it there and decide what to do next. My next step is to get rid of this e. So I always need to take the natural log of both sides to get rid of an e. So I'm just going to leave this in my calculator and hit the ln button. And then second n, this minus sign at the bottom. Do you see how it says ans on top? If I do that, that brings my last answer into that parenthesis. So I'm taking the ln of my last answer, which was at 31 point, all that stuff. So that gives me this. And again, it's not nice. So I'm not going to round it for real. I'm going to leave it in my calculator again and decide what the last step is. My last step to find K is to divide both sides by 8. So I'm going to just leave that answer in there and hit divide by 8. This is how you avoid rounding too early and messing up your answer. So now I'm going to round for real. So that is my K, which means my real equation for the rest of this problem is this times e to the K, which I now know, 0.43 times T. So here is the equation I'm going to be using for the rest of this problem. So how did we find it again? We used the initial value they gave us. But then since we did not have the K, we plugged in another point that we had. The T went here and the answer went here. And then we were able to solve for K. So part B says, estimate the global confirmed cases 10 weeks into the epidemic. So since our T is in weeks anyway, 10 weeks just means T is 10. So to find the answer at 10, that's what this means. We're just going to plug all of this into the calculator and see what we get. You should get a quite large answer, which makes sense if you remember what we used to know about COVID-19 and how fast it spread. So it was this many confirmed cases after 10 weeks. All right, and then C, at what rate? So here's my clue right now that I need the derivative. At what rate in cases per week was the number of global confirmed cases increasing at the start of week 10? So that's basically just asking me for the derivative at week 10. So let's go back to my initial equation and let's first find the derivative. That's 4,3. So the derivative would be all of this again, but then times the derivative of this, which is the 0.43. Or using our new equations, this is basically just K times f of x. So now if I plug in 10 to all of this, I should get my answer, which is a rate of how much these cases are growing per week. So this is my answer. So I'm going to round that now to about 2.8 million cases per week. So your final answer, if they're asking something about rate, should be some kind of number per something. So in this cases, we're talking about cases per week. How much is it increasing by? This many per week, which is crazy, which is why it was such a big deal, because that's how many more cases we were getting each week at that time. Okay, those are some examples on application problems using this uninhibited growth model. So feel free to let me know if you have questions on that or if you want to see any more examples.